Digital eye is a line balancing scenario. Even if it didn't mention designing an assembly line, you can kind of tell by looking at the data. Let's take a look at it. Digital eye must design an assembly line to produce a new line of slim digital cameras. Okay, assembling a single camera requires the completion of 9 distinct tasks, and this is what I mean by spotting a line balancing problem. There's these tasks that must be done to assemble a product. There's some precedence relationship information, and there's some information on how long the tasks take. Not only that, but look down here, this assembly line operates 8 hours a day to produce 576 digital cameras daily, and there's mention of a decision rule. Digital eye uses LPT, that is longest processing time, to create the design. Okay, fine. First question. What is the cycle time? What is the cycle time of digitalized assembly line? Well, we haven't designed the assembly line, but we remember in line balancing that ironically, you have to determine the cycle time of a line, basically the speed at which it will run, before you can design it. So we might as well do part A. We will have to anyway if we have to design this line. Okay, so how do you calculate cycle time? Cycle time, I'm just going to write CT. Cycle time equals operating time divided by demand. Essentially is how the D is explained. Now, operating time, this number here is how long you want the line to run, and that's what I underlined. It said something about they would like it to run for 8 hours a day. Well, perfect. OT for operating time, 8 hours a day, so I'll put an 8 there. And then D is essentially demand, what you demand out of the line during that time, what you need the line to produce during OT, however much time that was. And they said that. They said to produce 576 cameras, so that goes in the denominator. So cycle time in this particular case is essentially 8 divided by 576, and my calculator comes out kind of messy, 0.013. Whoops, that's supposed to be a 3, and then like a lot of 8s. Oh, right. And so you say, that's the answer. This actually is the answer, you know, divide 8 by 576 on your calculator, but be careful. I would not leave that alone. Okay, because what is that supposed to be? Well, the cycle time is the budget of time that each workstation will have to do whatever it is that we assign it to do. Okay, each workstation is going to have 0.01388, 0.01388 what? Hours. Whatever OT was in, that number, that is what the answer comes back to you in. The 8 in the numerator was in hours, so this is hours. Now, you could leave it, I mean, that's not very intuitive, but as far as an answer to this one question, oh, wait a minute. Actually, they're saving us. The question is specifying in seconds. Oh, so that won't do. But even if it didn't say that, when you are working a line balancing problem, you have to calculate the cycle time first. Don't leave the cycle time alone until it is stated in the exact same units that your duration data was given to you in. And notice that it is in seconds here. Okay, so that means we need a cycle time that's in seconds. That's not hard to find. We know what it is in hours, you know, and if you said, okay, well, that strange amount. If, for instance, you said that times 60, what you're going to get then is what it is in minutes, which is like 0.8333 minutes. And then if you say that, strange amount times 60 again, this is going to convert it into seconds. Basically, it is 50 seconds. That's what it translates to, 50 seconds. Oh, okay, so the cycle time of the assembly line should be 50 seconds. Each workstation will have 50 seconds to do whatever it is that's assigned to it. Fine. That part's done. What's the second part of this problem? Oh, how many workstations are required by this design and what tasks are done at what workstation? We have to design the line. just to answer that question. Actually, now we have to design the line. And you can see that pre-printed in this note frame here is the very helpful header for conducting line balancing, actually designing the line. You can remember how to do line balancing if you can remember station, time remaining, eligible tasks, eligible tasks that will fit, and assigned. Now, before we do that, there is another step. It's not, strictly speaking, required, but I find it very helpful. I wouldn't work a line balancing problem without completing this other step first. Now notice I turned back to the data. You know, we had that whole worksheet ready to go, and I put it away. I went back to the data because I want to draw a precedence diagram. A precedence diagram is just an illustration of this information. You say, well, why do you want to do that? Because it's so much easier to read the illustration than to keep reading the table while we're doing the line balancing, so I highly recommend it. Now, in a precedence diagram, you just draw visual representations for each one of the tasks, and you connect them according to the precedence relationships. You do that by beginning looking for the task that doesn't have any immediate predecessors, meaning that nothing comes before it. And I see here it's just this task A. It means it's the first thing that's done. I'm just gonna draw it. Okay, this is task A. Now I look for everybody that has task A as an immediate predecessor, and I see that it's B and C. I'm going to draw that. When you're done with A, you can go on and do B, or when you're done with A, you could go on and complete C. Now I keep working my way down the list. Notice that D, E, and F all have B as an immediate predecessor. This symbol represents us completing task B. And what we're saying is, when you're done with that, you could do D, or you could step off and do E, or F. Okay, now we're down to here. Task G has D and E as immediate predecessors. They both need to be finished before you can do task G. So I'm going to draw G right here. And I have to connect both D and E to G to represent that relationship. Okay, task H has C and F. Here's C, here's F. And whatever H is, when C and F are done, then you can complete H. And then task I has H as an immediate predecessor, so I'll just draw it there. You know, when that's done, you can go on and do this. Okay, that's the actual precedence diagram itself. One other thing that's very, very handy, I am going to simply copy the duration data onto the precedence diagram. I'm not calculating anything. I'm just looking up, like task A is 10 seconds. I'm going to write that. Next to A, it's 10. Task B is 30 seconds, so I'm just noting that. Task C is 25 seconds, so I'll write that. Task D is 18 seconds. It's over here, and 18. Task E is 5. Okay, 5. Task F is 17. Okay, 17. Task G is 37 seconds. 37. Task H is 30. Got it. 30. And then task I, one last one, is 12. All right. Now, this is a tool to help us in the actual line balancing. Time to design the assembly line. Going back where we were, right? We design assembly lines starting at the first workstation and adding however many workstations we need until everybody's got a home. All of the work is assigned. Starting at the first workstation. Time remaining. Here at the beginning, when no assignments have been made, I'm writing 50. Where did I get 50? The cycle time. I've opened up a workstation. I haven't assigned any work to it. Therefore, it has the entire cycle time available to it, and we determined that that was 50 seconds. Okay, eligible tasks. That means, according to the work that's already been done, what is available to be worked on? Well, right now, there's nothing has been done here. Nothing's been assigned. That means that only A, the task with no immediate predecessors, is eligible for assignment, which makes this a no-brainer. I mean, of course it's going to get assigned then to the first workstation. Now, task A, of course it'll be done at the first workstation. It has to be. We can mark it off the list. It's 10 seconds long. That means here at station 1 we have 40 seconds left, right? We could do something else, perhaps. Eligible tasks. Well, what could we do? Okay, A's done. We could do B, or we could do C. Okay, note that down. In terms of precedence relationships, B and C are both eligible. Now, what's this screen, eligible tasks, that will fit? We only have 40 seconds left at this station. That's what the check is. How long is B? It's 30 seconds. Well, it would fit in the 40 seconds. C is 25 seconds. It would fit in the 40 seconds. Okay, they both survive, so to speak. Now, only one of them can get the assignment. This is where your decision rule kicks in. And the problem had specified longest processing time. Oh, meaning that when you have a choice between here and here, you pick the longer of the two. Well, B is longer. It's 30 seconds, so it gets chosen. It gets the assignment. We now know where it will be completed at the first workstation. Okay, it's 30 seconds long. That does mean we have 10 seconds left at the first workstation. We have 10 seconds left. Who is eligible? Well, we're still trying to find a home for C. It's still eligible in terms of precedence relationships. Now that we've completed B, that's opened up D, E, and F in terms of next steps. List them, D, E, and F. Now, this is precedence relationships. These are all next steps that are allowable, but there's only 10 seconds left at this workstation. Which one of them would actually fit? C is 25 seconds long. It won't fit. D is 18. It won't fit. E will fit. Okay, F won't fit. So of that crowd, only E will actually fit. So no brainer. E gets the assignment. That means we have 5 seconds left. I better mark E off. E has been assigned. Now, who's eligible? Well, there's still everybody we're trying to find a home for. C, D, and F. And you might be thinking, oh, well, if you're just talking about next steps, you have to list G, right? Because we've done E and then we go on to G. And the answer is no, never do that. Because G has 2 immediate predecessors. See how there's 2 arrows? And it can't be eligible until they're both done. Anyway, none of those are going to fit anyway. We have 5 seconds left at this workstation, but we're going to close it. That's the best that we can do. It's full. We can't find anybody who's eligible that will fit in the time remaining. Oh, all right. Now what do? Open another workstation. Open another workstation in our design, the second workstation. There's a full 50 seconds remaining. We have still the same crowd looking for a home, C, D, and F. They'll all fit because we're starting with a fresh workstation. I don't even have to check that. But, okay, we have to pick who's longest. C is 25, D 18, 17, C. C gets picked. Okay, and C is 25, so that's going to knock this down to 25. That's going to knock C off the diagram. Who's eligible now? Just because C has been done, we can't go on to H because I noticed that H again is connected to something else that's important. That means that it's still only the other 2 that are eligible, D and F. There's 25 seconds left. Either one of them will fit. There's 17 and 18 seconds, so we have to then pick the longest. That would be D, the 18 seconds. Okay, so D gets the assignment. That only leaves, what, 7 seconds left at this workstation? D's been assigned. Who's eligible in terms of precedence relationships? Well, F is eligible. Actually, G is eligible now. See how D and E are now done? You can start adding G to the eligible list. But, I mean, none of this is going to fit because we only have 7 seconds left. We pulled a blank there. It's time to close this workstation. Time to close this workstation and open a new one. Our third workstation, a full budget of 50 seconds. We're still looking for a home for F and G, so we can just hand that down. Now they'll fit. So the question is just which one of them. So we better check which one of them is longer, and that would be G, the 37 seconds. So G goes ahead, gets the assignment. Let's see, G gets the assignment, so this whole upper part of the diagram is done. We are still looking for a home for F. G is 37 seconds long, so let's see if I can do this in my head. That means that there's what, 13 seconds remaining here at this station? F is 17 seconds long, so it's not going to fit in 13. No, it's not going to fit. Well, that was fast. We have to close the third workstation. It's full. Open a fourth workstation. Full budget. 50 seconds. Still looking home for F. Finally, F gets to go ahead. F gets assigned. F was 17 seconds. F is 17 seconds, which means that there'll be 33 seconds left. Now, who's eligible now? F is finished. Well, finally, now that F is finished, now we can add H to the list because both C and F have already been assigned. So now H becomes eligible. Will H fit? It's 30 seconds long. Yes, it will fit. Oh, okay. So at least it will fit at this workstation also, leaving 3 seconds. At the point that H is done, there's one last one and it becomes eligible, and that's I. But there's only 3 seconds left, and I is only 12 seconds long, but it's not going to fit, so we have to close this workstation, open a fifth one, 50 seconds, just as a home for I. It's only 12 seconds long, yes I know, but we have to because it's got to go somewhere. So this is actually our design, right here. Now what were the questions that was asked? It says, this is the design. It says, okay, how many workstations are there in the design? Well, you can see that by the time we were finished. There's 5. Okay, so this assembly line has 5 workstations. What else does it ask? What tasks are done at what workstation? If you're looking at somebody's scratch work for line balancing, it's right here in the assigned column. We'll do A, B, and E at the first workstation. We'll do C and D, task C and D at the second. The third one just does task G. The fourth workstation will do task F and H, and then the fifth workstation only has to do task I, that little short task, meaning that there's 38 seconds left over there, but that's the design. Okay, so that part of the scenario is done. What other questions? Which workstation enjoys maximum idle time? Oh, better haul the scratch work back out. Where do you find that? The idle time at each workstation. The idle time at each workstation is that leftover little number that you couldn't find any use for. For instance, there's 5 seconds of idle time at the first workstation. We abandon it there. 7 seconds here, 13 seconds here. Only 3 at the fourth workstation. Yeah, the one with the most idle time is that station that we had to tack on to the end just to do that one last task. Okay, 38 seconds of idle time. That would be the fifth station. Or station 5. All right, station 5. How efficient is the design? The efficiency. How do you calculate the efficiency of a design? Well, think about it this way. It's a formula. Efficiency equals the sum of the tasks times divided by the cycle time times the number of workstations in the design. Oh, so I'm going to need to track down some numbers. first this number, I wrote ST for the sum of the task times. We have to go back to the data. Won't be difficult, but we need to add up all these numbers. You add up all the task times. For this problem, you do that. I get 184. Okay. What is that number supposed to mean? It means that if you had to assemble one of these slim cameras by yourself, it would take you 184 seconds, because it's the sum of all of the different tasks. All right, that's also what we need for the numerator, so let's carry it over. 184. The cycle time is that 50 seconds we've been working with. The number of workstations we were just remarking is 5. That will calculate the efficiency of this design. So I got 73.6% efficient, because on the calculator it says 0.736. Now it also asks what's the balance delay. Balance delay is easy, especially if you've calculated efficiency, because balance delay is just the opposite. It's 1 minus efficiency. Okay, so if it's 73.6%, then the balance delay is the opposite of that, or 26.4%, or 1 minus 0.736. And I think if you have the first edition of Simpson and Hancock in the answer key at the back for that one problem, I think that the balance delay is wrong. I think that they report the efficiency twice. Anyway, balance delay, super easy, opposite of efficiency. 1 minus the efficiency. Okay, so that sorts that question. How does the actual number of workstations required by this design compare to the theoretical minimum number of workstations? Okay, now the actual number, we keep saying this, but I'm just writing it down as notes. It's 5. There's 5 stations in our design. The theoretical minimum is a formula. You take the sum of the task times and you divide by the cycle time. Okay, well, we've retrieved the number for the sum of the task times. That's 184. We said the cycle time was 50. So my calculator, I get 3.68. With this formula, the theoretical minimum number of workstations, there's a rule. Always round up. That's what those strange brackets mean. Always round up. You're going to report a round number if you're asked what's the theoretical minimum number, and that number will be the result of rounding up. Now, this particular problem, we said I would have round up anyway. Yeah, fine. But even if it had been like 3.017, you would have needed to have rounded up to 4. Okay, so the theoretical minimum number of workstations is 4. What's that mean? It just means that no matter how hard you try with this problem, we know that there is no design out there that has 3 or fewer. There might be one that has 4, we're not sure, but we know for a fact there's no way that you would get this work crammed into 3 workstations. Now, what the question asks is, it just asks how does this compare to what you actually did when you designed it? Well, our design had 5, the theoretical minimum is 4, so, you know, I don't know, actual has 1 more workstation than the theoretical. It has 5 versus 4.